everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. And we generate a ton of news on Universe Today, and that turns into a ton of questions from you about the topics we cover and just general topics, mostly about Lagrange points. But there'll be some non-Lagrange point questions, I'm sure of it today. Now, we've got a little bit of things to catch up on. We introduced a new idea in a previous question show where we had codes go beside each of the questions as I answered them. And this week, everybody voted for what they thought was their favorite question back in episode 180. And the winner was Timberwolf, with a question about humans surviving in the low gravity on Mars. So congratulations, Timberwolf. It was a great question. I guess I gave a great answer. We were a good team. So congratulations. So again, we're going to run a code beside each one of the questions. Now, I said it was going to be down below, but it ended up being up high. That's confusing, very embarrassing for me. So there will be a code somewhere on the screen. And so either just punch that code into the YouTube comments, or as you're asking a question or commenting, put in the code. We'll count them all up and I will announce the winner. So you've probably noticed we've added a new segment here to the channel, which is Space News Bites. We're still workshopping the name, but let us know what you think. So we did the second episode. This is about the Uranus mission, Space Launch System, a bunch of other stories. We incorporated a bunch of the feedback that you had to give us, so thank you very much. Please, still a work in progress. Is the length right? Do you like the depth that we're going into the stories, graphics? Please keep giving us the feedback, but the plan right now is I'll record a new one of these probably every Friday, just after I finished off my newsletter, and then we will post it live probably Saturday, Sunday, depending on how long it takes to edit. You know, news, it's got a pretty quick turnaround. So definitely check that out. Let us know what you think. And the last thing that I want to mention, we announced this in the news show, which is we've been sort of hovering at around the 800 to 900 patron mark here on the channel and with Universe Today in general. And we want to try and make it go a little higher, see if we can reach the 1,000 mark. And the timing is that both Space Launch System and Starship are attempting to launch probably in the next few months. The question is, can we beat them? Can we be in a space race with SpaceX and NASA to be the first one to hit 1,000 patrons here on the Universe Today channel? So if you want to be a part of that, there's a reward, which is that a bunch of people have been asking, will I do some kind of book club, read some books with you, give feedback? And so if we hit 1,000 patrons, we'll do it. I'm not sure what it will look like, but we will do something related to science fiction books here on the channel. So go to patreon.com/Universe Today and sign up and help us reach that 1,000 mark before Musk and NASA get there. All right. So apart from that, let's get into the questions this week. Gaurav Sharma. Can James Webb use gravitational lensing to look all the way back to just moments after the Big Bang? We've been hearing more and more stories about the Hubble Space Telescope and how it's been able to see right back to just a few 100 million years after the Big Bang. And normally Hubble can only see out to a few billion years after the Big Bang. But to really see the greatest distance with Hubble, you need to take advantage of gravitational lensing. So you've got these giant galaxy clusters that are out there in space. And when things line up perfectly, when there's a background galaxy that lines up perfectly between the galaxy cluster and us, when they're all lined up, then the galaxy cluster acts like a natural telescope in space. It acts like a lens. And any objects that are behind it are magnified a lot. And so galaxies that would be previously completely invisible to Hubble are now these weird blobs on the outside of this galaxy cluster. And then astronomers can use computers to essentially reconstruct what that galaxy is and understand it, study it, even figure out what kinds of elements are in it. And the records just keep getting broken. Hubble keeps going back and back and back. And we're well under 500 million years after the Big Bang. So 13.2 billion years ago is how long the light has been traveling. And in fact, just within the last couple of weeks, astronomers saw a star that, like one individual star that was at that kind of ludicrous distance. And so the question you're kind of asking is, when James Webb, with its vastly more powerful optic system designed to look at those high redshift galaxies, the distances that are moving away from us faster and faster. What will it be able to do with gravitational lensing? Will it be able to see the Big Bang itself? And the answer always is no. You can never see the Big Bang itself in electromagnetic radiation, in visible, optical, in infrared, ultraviolet, radio waves, never. And the reason is because for the first 380,000 years after the Big Bang, the universe was opaque. It was literally like it was the inside of a star. And you can't see inside a star from the outside because it is opaque. But after 380,000 years, the entire universe had cooled down to the point that it became transparent. Light was released out into the universe, and we see that as the cosmic microwave background radiation. But there was some stuff. The universe got up to some shenanigans between when that first light was released, and the universe was just entirely primordial hydrogen and helium, and the larger, more complex galaxies that Hubble is picking out. There had to have been the first stars that were formed after the cosmic microwave background was released, but before these fairly large, surprisingly mature galaxies were coming together. And the answer to that question is that they're called these population 3 stars, and they are essentially pure hydrogen and helium left over from the Big Bang. They probably lived fast, died hard. They could have been hundreds of times the mass of the sun, possibly 1,000 times, possibly tens of thousands of times the mass of the sun, and then exploded as supernova, seeding the rest of the universe with heavier elements and sort of beginning this process of nuclear synthesis to the point that we get the heavier elements and the more, I guess, metal polluted stars that we see today. And so the question is like, will Webb be able to use gravitational lensing in the same way that Hubble does to be able to see those first stars? And the answer, and I love this, is yes. When you get a perfect gravitational lens, then you're going to be able to magnify the capability of James Webb by a factor of about 10,000. And that is enough, theoretically, hopefully, to see some inkling of the first stars. Now, it's going to be exactly the same as what's happening with Hubble, where you've got to have that perfect alignment, and you only get the stars and the galaxies that the universe is lining up for you. But still, we should get those first hints of what those first stars were, thanks to gravitational lensing. Future telescopes, bigger versions of James Webb, should be able to see those first stars directly. But Webb will be able to get those first hints of what happened with those first stars. And it's a fascinating question because we literally just don't know what the first stars in the universe were like. There are none left. They can only be modeled in computer simulations, and this will be the way that we'll be able to find out about them. Liam O'Reilly, do you think that dropping antimatter or dark matter in a black hole would do anything? Sure. Dropping either antimatter or dark matter into a black hole would increase the mass of the black hole by the amount of the mass of the antimatter or the dark matter that you dropped into it. And we get this question a lot about antimatter. People say, like, could you use antimatter to destroy a black hole? And the answer is no. Let's say you had a star that was 10 times the mass of the sun, fully made of antimatter, and you fed it to a black hole, and the black hole was 10 times the mass of the sun. You would end up with a black hole that had 20 times the mass of the sun. It would gobble up that antimatter star and gladly add its mass to its own. And when you think about this process, like, what is antimatter, right? Antimatter is the equivalent of matter, has an opposite charge. When matter and antimatter interact, they release an enormous amount of energy. They annihilate and release essentially pure energy in the form of gamma radiation. And yet, if you could take a whole bunch of gamma radiation and compress it down into a small area, you could turn that into a black hole. And black holes are perfectly fine to feed on photons of light that fall into them, photons that come from the cosmic microwave background radiation, cosmic rays, particles, antimatter, anything. Anything that goes into a black hole just adds to the mass of the black hole. Now, we don't know what dark matter is, but we know that it has mass. So if you add mass to the black hole, black holes are very good. They have one job, which is to get more massive as they consume things. So we don't know what dark matter is, but we can be pretty confident that if you added it to a black hole, you just end up with a more massive black hole. Gallus 1. If an alien civilization had the technology to travel from another star system, is it not reasonable to assume that they could also have a technology that keeps them hidden from us and our ability to detect them? Maybe, sort of. So, like, the important thing when you think about are aliens traveling from star system to star system, or even do aliens exist? The first assumption that you have to make is that they have to adhere to the laws of physics as we understand them. In other words, they have to give off waste heat. They have to, for every action is an equal opposite reaction, that they have to adhere to gravity. All of the laws of physics as we understand them will have to apply to the aliens as well as us. And if you're not willing to make that conceit, then the aliens can do anything. It's effectively magic, right? Are the aliens propelled by unicorn tears? Possibly. Who knows? But if you can say, okay, they have to adhere to the laws of physics as we understand them, then if you're going to be moving a starship from one location to another location in the universe, you're going to have to expend an enormous amount of energy. Either a laser sail is going to be zapped, and you're going to have to essentially funnel almost the entire radiation that's emitted off the star into this one very precise point, and it will be very obvious. Or the starship has some incredibly powerful drive that is harvesting fusion material, or maybe it's got antimatter. It's going to get off this enormous amount of waste heat. And as that spacecraft is flying towards the Earth, it's giving off heat behind it. And then the spacecraft has to turn around at the halfway point and decelerate itself. And so now the thruster is pointing directly at the Earth, and it's giving off ludicrous amounts of waste heat. We could see that. We could see this really weird thermal infrared signal that's happening in the sky and go, something's coming our way. And so it's like, okay, yeah, and if the aliens have the technology that don't use the laws of physics as we understand it, then whatever, like we can assume whatever we want. So who knows? So I think that's like the first part of the answer, is that, like, what else can we do but look for things using the laws of physics as we understand them? Like, yeah, by all means, we could imagine things that we can't imagine, but how do you do that? It's tough. It's really tough. So you start with imagining things that you can imagine, and then later on work on imagining the things that you can't imagine. But would we expect an alien civilization to quietly, secretly travel from one star system to another star system to watch us carefully and, I don't know, build up a record of humanity's advancement and eventually welcome us to the galactic civilization? No, we wouldn't expect that, because, and I did an interview with Dr. Robin Hansen a couple of weeks ago, and we sort of talked about this idea that this concept of grabby aliens, man, that needs some workshopping. But anyway, this concept of aliens who will expand outward at relativistic speeds, literally as fast as the laws of physics will allow them. We would see them in the sky as these expanding spheres of how they would change the environment of the space, how they would turn what were before stars and planets into Dyson swarms, how they would start rearranging stars into locations that are more amenable to what they want. And we might see one over there and then another one over there, and we know, at some point they're going to interact with each other, and the sparks are going to fly. And so you could absolutely have some civilization that all it wants to do is quietly send one little spacecraft with one intrepid crew that's there to make first contact. But then you got the grabby aliens just expanding out at just about the speed of light, harvesting tens of thousands of star systems per year, and they would just be lost in the noise. So yeah, it's entirely possible, but it's more likely that we're just going to get overtaken by one of these expanding civilizations as they sweep past us at 80% the speed of light. there could be countless numbers of quiet civilizations, but it's the loud ones that we'll notice. Chris Rhines, if black holes shrink through Hawking radiation, do they not also lose mass? And how do they not lose enough mass to no longer be a black hole? Hawking radiation is this idea from Stephen Hawking that black holes can emit radiation from their surface and they evaporate. And the science is very complicated and it's more of a particle physics answer. And I'm not great. I don't have a really nicely rehearsed, here's why Hawking radiation happens. But, we've done episodes about it. Lots of people have done episodes about this idea. So we're just going to sort of assume, right? You've got a black hole. You've got various particles that are being evaporated, that are being released from your perspective from the event horizon of the black hole. Mostly it's photons. You're mostly seeing heat. And so it gives the black hole a temperature. And the larger the black hole, the more massive the black hole is, the larger the event horizon is, the colder that temperature is. And for the most massive black holes, they're going to be kept from really evaporating or losing any mass because they're gathering the background heat from the cosmic microwave background radiation. But eventually the background will cool down to almost absolute zero, and even those really massive black holes will start to evaporate. And as they evaporate, they'll get smaller and less massive as their mass is given off in radiation. And over time, as the black hole gets less and less massive, its heat, its temperature from an external perspective starts to go up. And as you get closer and closer to, say, the mass of an asteroid, it starts to pick up really quickly. The mass of a house, now your black hole is starting to look almost room temperature. But it's still black hole. It's still the mass of a house compressed down to such density that it remains a black hole. And then it gets down to the mass of, a car, right? And it's still a black hole. And the temperature gets hotter and hotter and hotter. It gets hundreds of degrees, thousands of degrees. And then in the end, it just gives off one final flash of gamma radiation, which is like the highest energy that it can release, and it's gone. And so it never unblack holes into a neutron star and then unneutron stars into a white dwarf. It's just black hole right until the last moment. And what we would perceive as these black holes were evaporating away is these flashes of gamma radiation out there in space. And I did a great interview with Celeste Keith about primordial black holes just a week ago. And you should definitely check it out because we talked about a lot of these topics about how can we detect these primordial black holes? How long will they take till they disappear? And so on. And it's a pretty cool idea. Futurism memes. Hey, Fraser, why don't supermassive black holes suck anything up? Well, black holes don't suck. Yeah, they're pretty awesome. So they don't suck. But we imagine, or somehow people imagine, that black holes are like these vacuum cleaners that are sucking in whatever, the entire universe. But the reality is that for all intents and purposes, a black hole is just an object of mass. And you could replace the sun with a black hole of exactly the same mass, and all of the planets would just continue to orbit around this black hole. They wouldn't be sucked into the black hole. They would just orbit around it forever. And so the supermassive black hole at the heart of the Milky Way, it is just an object with a lot of mass that various stars are orbiting around it. And it's not sucking anything in. Now, stuff does collide with supermassive black holes, and you get when a planet or a star goes into a black hole, you get this blast of radiation that comes out of it because it got too close. But it's kind of in the same way that if you got too close to the sun, you would fall into the sun. If you got too close to the Earth, if the moon got a lot closer to the Earth, it would go past the Roche limit, where the near side of the moon is pulled so strong, much stronger than the far side of the moon, that it gets spaghettified. It gets torn into pieces. It's stronger than the material strength of the moon can hold it together. And the moon would be torn into this ring, and this ring would go around the Earth, and then all the parts of the ring would be torn up, and they would all collide with the Earth, and you would end up with no moon and a very bad day for the Earth. And it's the same thing with a black hole. It's the same thing with the sun. It's the same thing with the supermassive black hole. It's just gravity doing what gravity does. Anonymous Freak. At what point would you consider going to space? I've mentioned several times in the past that I'm not super excited about going to space. Like, if you offered me a 1-week trip to the International Space Station on a Crew Dragon, I would take it. You know, if you're willing to pay my $55 million ticket, I would do it, because Crew Dragon seems pretty safe. Space Station seems pretty safe. The view sounds incredible. The experience would be mind-blowing. I would do it. If you said I had to go to space and I could never come home to Earth, I would turn you down. If you said I could go visit the moon for a week, I would do it. But if I had to live on the moon, I would say no. And I definitely wouldn't make the trip to Mars. It's just like 3 years of space flight. I wouldn't do it. So I think it's going to have to become ridiculously cheaper for me to be able to afford it, and safe. And I think just like short term, I really like Earth. I would love the experience. I want to see Earth from orbit. That would be amazing. I mentioned in the news show a couple of weeks back this idea of the space perspective, that they've got this balloon. I'm coordinating an interview with the people from Space Perspective. I'd do that. That sounds great. Like, very high altitude, see the curvature of the Earth, but come home in time for dinner. That sounds very civilized. More questions in a second, but first I'd like to thank our patrons: Doug Waters, Stuart Mills, Texas Knight, Gaurav Sharma, Don Novak, Lee Newland, and the rest of our 879 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday and help us beat SpaceX and NASA to space by helping us get 1,000 patrons before they launch either of their rockets. Go to patreon.com/universetoday. And if we cross that mark, we'll figure out the book club. SpongeBob. What telescope do we need to see continents and detailed features on other planets in some of the closest star systems? When will it possibly happen? Say it with me, everybody. You need a solar gravitational lens. And I just did an interview with Dr. Slava Turishev like a couple of weeks ago, and it just keeps coming up. Isn't that weird that I just keep interviewing the people who have all the answers to the questions that you want to know more about? So he is with NASA, and he's working on this idea of a solar gravitational lens, this idea of sending a spacecraft out to about 550 astronomical units away from the sun. And at that point, the sun acts like a natural gravitational lens. And you would, with that, be able to see features on the surface of an exoplanet like Earth, 100 light years away, with startling detail. You would have a megapixel image, something that's like 1,000 pixels by 1,000 pixels of one planet. You would see the clouds and the mountains, and you would see the oceans and the rivers and the lakes, and you would see evidence of cities and air pollution and all kinds of things. And in my interview with Dr. Turishev, you would need to build a telescope that was about 90,000 kilometers across, a space telescope that would be able to provide that same kind of resolution. So for the future, really, the only way that we're going to be able to get that kind of high level quality is to send a spacecraft out to 550 plus astronomical units away from the sun, and to be able to image these exoplanets. One spacecraft per planet that you want to take a look at. And just for perspective, like Voyager 1 was launched in 1977, and it is about 200 astronomical units out, and has been traveling for, what's that, like almost 50 years. So in 50 years, we can go about half the distance that we need to go. So it's a big job, but the results could be really worth it. Just a 1 meter telescope would give you images of that high quality. Eric C. When people are in space, they sometimes get flashes of light from particles hitting their retinas. Is it possible for this to happen on Earth, or is the atmosphere too thick? Yeah, I've had a chance to talk to astronauts about this, and it is unnerving. So when an astronaut is in space, in the International Space Station, and they close their eyes, like say they're going to sleep, they see these flashes occasionally in their eyes, and that is from cosmic rays hitting their retinas and causing these flashes. And it's a stark reminder that we live in a universe filled with cosmic radiation that is trying to kill us. And as you come down through the atmosphere. As the atmosphere gets thicker and thicker and thicker, you are protected by the atmosphere of the Earth, you're protected by the magnetosphere of the Earth, and we don't see that. I mean, it's possible you occasionally do. I mean, cosmic rays do make it down to the surface of the Earth, but a fraction, like about 10% of what the astronauts experience. And the astronauts are mostly still protected by the magnetosphere of the Earth. They get about 10% of what someone in deep space is going to experience. So you just imagine, like if you were on a trip out to the moon, you would see these flashes in your eyes even more common, and you would just be like a non-stop reminder that you're getting bathed in radiation that is increasing your cancer risk down the road. Stand-up comedian Joe Walters. How is it possible NASA flew a craft anywhere near the sun? I'm assuming you're talking about the Parker Solar Probe, and we've done a whole video on the Parker Solar Probe, and it is getting incredibly close to the sun with each one of its orbits, and that's its job. Its job is to observe the sun, and the best place to observe the sun is to get really close to the sun and observe it from there. And like, how can it survive? If you look at the Parker Solar Probe, it has this enormous heat shield in front of the spacecraft. And as each orbit that it does, it has a very elliptical orbit. And so most of the time, Parker is spending its time pretty far away from the sun. But then it falls down on this very elliptical orbit, gets closer and closer to the sun, turns this heat shield, and then keeps the heat shield in between it and the sun as it whips around the sun. It absorbs as much heat as it can, and then just as it can't absorb any more heat and it's about to start cooking the spacecraft and melting its electronics, it flies back off into space, radiates this heat away, sends the images that it took back to Earth, sends the data back to Earth, and then gets set to do it again. And you can imagine with each one of these orbits, NASA is learning more and more about the actual heat that the sun is putting out, how the spacecraft is performing, and they're just going to keep pushing the spacecraft closer and closer and closer to the sun, each time getting better data, better images, better analysis. It's going to pass right through the sun's outer atmosphere, and they'll push it right to the brink, I'm sure. That in the end, when Solar Probe has finished its main observing mission, the goal will just be, what can we get away with this spacecraft? Jamie Shepard, do you think the density of stars, matter, and usable energy should be considered when we think about Type X civilizations, aka become more efficient, as moving resources across the cosmos is inconvenient? There are limits that even incredibly advanced civilizations are going to have to deal with the laws of physics. And I mean, again, back as I mentioned earlier on, like if they don't have to obey the laws of physics, then there's no rules, and they can use their unicorn tier drive to move stars at 10 times the speed of light and do whatever they want. Whatever your imagination can imagine, you can't imagine the imaginings. But if they do have to live in the universe, then they're stuck with the universe that they get. And there's a couple of constraints. Like, one is we live in this expanding universe that a lot of material is falling away from us or moving away from us faster and faster and faster. In fact, 94% of the universe that we can see is unreachable. Even if you could go the speed of light, you couldn't reach 94% of the universe. That leaves you with 6% of the universe, the explorable universe, the empirable universe, I guess. And parts of that stuff is hurtling away from us faster and faster. And so you can imagine if an alien civilization wants to keep its empire coherent, it's going to need to start bringing the material together to try and stop it from getting away from them. And, there's lots of ideas on how you could, you can move stars around. You can build a shell on one side of a star, and the star emits radiation on the shell, but it's also gravitationally attracted to the shell. And then the star is essentially pushing itself around the Milky Way. You can imagine, over the course of a few billion years, you could move a star pretty much anywhere you wanted inside the Milky Way. And so you could imagine over a few billion years, an alien civilization has rearranged all the material in their galaxy into whatever form is the most economical for being able to move around. And maybe they've done the same for all the dust. They've gathered up all the dust and gas and put them into places and parked them and put them in Minecraft trunks. I don't know, chests. But there's going to be limits to the laws of physics, limits. There was a really interesting stat that I read that every second that goes by that we don't create the universe that fills the reachable, that 6% of the observable universe that I mentioned, 10 to the power 14 lives, human beings, fail to exist for every second that goes by that we put this off, that we could save 10 to the 14 lives if we got about building this giant civilization sooner. So they will be constrained by the resources they have available, but they will have incredible ability to move things around, to rearrange galaxies how they see fit. And in the end, they will come up with whatever is the structure that makes the most sense for the kind of civilization that they want to create. Roland Mine, are you worried about solar flares? What do you think Earth will encounter in the next 50 years? Sure. Yeah. I think solar flares are one of the greatest threats that we have to modern civilization at this time. We have this giant interconnected electrical grid across various continents. We have satellites that are prone to solar storms. We have electronics. We have devices that are connected up. And when a solar storm hits the Earth, it can jam electrons through electronic devices and cause a surge that can destroy them. And the more stuff that you have connected together, the more dangerous that is. And any big break in an electrical grid, as we've seen, takes off huge chunks of it and everyone's power is out. So the solution is microgrids. The solution is to have like your home produces your electricity from your solar panels and you power your car, and then the chances of the solar storm causing your house any damage is very low. And then maybe you have a neighborhood and all of the people are connected into a microgrid among all of you, but you're kind of isolated from damage that could happen to other grids. And this is sort of a trend. This is a direction that we're moving just in general as we get solar, wind, various renewable energy resources, various methods of storage, that we're going to move away from these giant grids to microgrids. And so this is a problem that will eventually sort itself out. We will be far more protected against the dangers of solar storms. But right now, where we stand, we've got a lot of electronics and it's all interconnected, and it's sort of a bad place to be. So we need to hurry and get to that microgrid era of power, storage, and generation. Roger M. What would be the increase in resolution putting Hubble orbiting Neptune's moon? I mean, if you wanted to observe Neptune, putting Hubble out by Neptune's moon would be great, be perfect. And if you wanted to observe any of Neptune's other moons, then that would be the perfect spot for the Hubble Space Telescope. But if you wanted to look at anything else, like anything else in the solar system, then it's not going to be that helpful. So even though Neptune is pretty far out in the solar system, and you can imagine it gets closer to Pluto than we do, it can also get a lot farther from Pluto because it can be on the other side of the solar system. And now you've got to add the distance from Pluto to the sun and then the sun to Neptune, and that's really far away. If you average out the distance to all of the places in the solar system, the planet that is the closest to everything is Mercury. So the best place in the solar system would be a space telescope that if you wanted to observe most things at most times, you would put it at Mercury. But practically speaking, the best place is you put it around Earth because that's where we live. It's very easy for us to launch space telescopes and put them into orbit around Earth relative to sending a mission all the way out to Neptune. You can end up with a much smaller telescope out at Neptune. There's one caveat. There is dust in the inner solar system. And as you get farther and farther out in the solar system, out by Neptune, out by Pluto, that dust is less obvious. And the NASA's New Horizons spacecraft took some images when it was flying out beyond the orbit of Pluto, and they were able to see the universe with a level of clarity that we just can't see even with a bigger telescope. But it's only a certain kind of aspect of the universe, essentially the background heat and dust of the universe. Once it was away from the dust in the inner solar system, it was able to see what the universe kind of really looks like from that perspective. But That's about it. So there's real value in putting, say, a 1-meter telescope out beyond the orbit of Saturn to make very specific kinds of observations about the dust and heat in the universe. But beyond that, the best place to put a space telescope is the most convenient. Color and motion. I moved to a remotish area in Ontario last year. I'm just getting into astrophotography, but my gear isn't great. What's the most interesting thing that I could point a lens at this summer? Well, there's sort of like two parts to this. One is the summer, like this year, it is looking really good for doing planetary observations. And so Saturn, Jupiter, Venus, some of the other planets are starting to get Mars. They're starting to get bright in the morning right now. And so we may get to a point where they're quite well positioned over the course of the summer. So they're always the best to look at. If you're looking to do more deep sky astrophotography, then summer is one of the best times because that's when the core of the Milky Way is visible. And especially to us here in Canada, I only get the core of the Milky Way visible during just the summer months. And you only get a couple of months to view it, and some of the best objects, the Lagoon Nebula, the Trifid Nebula, there are just a lot of great globular star clusters. So summertime is nebula time, and you can practice taking images. Like the Lagoon Nebula is one of the brightest nebula in the sky, apart from maybe the Orion Nebula. And so I would just practice with those. But like, it's a target-rich environment. Set up your telescope, get a star chart handy, get a list of objects, and then just start observing them one after the other. Andromeda is great. M31 is beautiful. And you'll quickly learn what your limitations are as an astrophotographer, and then you will develop a plan to improve your work. That plan could very well be buy a better telescope, buy a better camera, etc. But a lot of the times there's just this balance between the gear that you have and just your technique. And as you get better and better and better at taking pictures, the gear becomes less and less important, but always pretty great. But congratulations on getting into the hobby and having nice dark skies. I can't imagine. I'd go crazy without having access to dark skies and being able to see the Milky Way every night. Like, I walk outside, I look up, I see the Milky Way. It's the best. So good. Congratulations. Let me know how your pictures turn out. Lily Pickard. Does the sun's gravity pull us closer to the sun every year? No. Is the sun pulling us closer and closer every year and we're eventually going to spiral in and crash into the sun? No. We are in perfect balance where we are orbiting around the sun. The gravity from the sun is pulling us inward, and our orbital velocity is applying a force outward, and those two forces are in perfect balance. Now, we follow an elliptical path around the sun, so it's not a perfect circle. Sometimes of the year we are closer to the sun, and other times of the year we are farther away from the sun. Weirdly, the closest time is when it's winter in the northern hemisphere, and the farthest is when it's summer in the northern hemisphere. But the Earth just follows this exact same ellipse, roughly, year after year after year, and has done so for billions of years and will continue to do so for billions of years until the sun dies, expands as a red giant, and possibly consumes the Earth. So don't worry about it. DL Recca, any word on the next viewable comet like hale-bopp? I miss seeing that. So I saw hale-bopp and I saw Hyakutake, and they were both in the late 90s. And I'm sure for some of you weren't even born. And they're amazing. They're incredible. Like, Hyakutake was this giant comet that you could see at the horizon when I saw it. Very bright nucleus, this huge tail that stretched up many degrees. Maybe I'm sort of overly romanticizing as I sort of think back and remember, but it was stunning. And we have not seen a comet that good in now 25 years. That's not fair. The universe owes us a really bright, spectacular comet. We've had a few comets visible that you could see with like the unaided eye, but nothing like these bright comets. And even those are nothing like some of the bright comets that people have seen in history hundreds of years ago. It's not fair. The universe owes me a comet. It owes you a comet. The universe owes us all a bright comet, and it needs to deliver, but not too bright, not too close. They're random. You get them when you get them. And so when I tell you there's a comet here and it's time to go look at it, drop everything and make sure you get a chance to see this comet, because you may have to wait 25 years before you get to see another bright one like this. Striatic. What is the cutest nebula? I'm going to go with the Pac-Man Nebula. I mean, everyone knows that the Rosette is my favorite nebula, but is it the cutest? No, I think the Pac-Man Nebula is pretty cute. Although, like the Snowball Nebula, which looks like it's just a tiny blue ball, is pretty awesome. I like Planetary Nebula the best, I think. And I would say the Snowball Nebula is like my favorite of the Planetary Nebula. The Ring Nebula is easy to see. The Helix Nebula is even easier to see. But there are a few really cool, really tiny nebula that are quite fantastic. So cute, I'm going with the Snowball Nebula. All right, well, those are all the questions that we got this week. Thank you, everyone, for asking the questions in the YouTube comments, the people who showed up for the live show. We do the show every Monday at 5 p.m. Pacific time. And remember, we put a code beside each one of the questions. So go ahead and mention the code in the comments below, and we will give a shout out to the person who was the best question asker. Thank you. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to university.com/newsletter to sign up, and it's totally free. And did you know that all my videos are also available in handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to university.com/audio or search for University on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and special thanks, as always, to Chad Weber, Nancy Graziano, and Anton Posnikov.